Okay. Good morning, everyone. Today, inshallah, we will start on a new topic, which is vector spaces. I will do it as an introduction for today. Although I have recorded this session last week, but still we are in parallel with lesson. They will start this week the part with vector spaces as we are going to do. It's really very important to go through all the previous chapters because you will use it as tools during this chapter. So it is the easiest part to use your tools in this chapter. The new concepts, it's really very simple, but you need to feel it. First of all, you need to understand it very well. Then you will need to feel how to work with it comfortably. I will start with some definitions. Of course, as you know, all the course notes and references already exist for Moodle. And also I've shared the last couple of slides that was sent yesterday to you all on WhatsApp. Okay, we will start introduction for vector spaces. Those symbolizations are important through our discussion in vector spaces. First of all, the above arrow or the card, it means and. So when you see X and you have an upper arrow like this, it means X and Y. So also the dot may be reflected as and. It depends on the statement that you are reading. I'm sorry. The plus, it means an addition between two coordinates in the concepts that we will face. And also stand for both A, X, and Y. This vertical line stands for all. And I will send you these slides. Stands for all. So when you see X vertical Y, it means X or Y. Also, remark this, for the arrow, but it looks down, which looks like V. It means all. So remark, when the arrow is up, it means an and. When the arrow is down, it means all. So this is X and Y. This is X or Y. This is very, very important. Also, this symbol, it's equivalent. And it means also F and only F. You will find examples on the right side, in front of each of them. This implies or implication, and also you will have it. This is, of course, belongs to, doesn't belong to. Of course, if you have this sign, which means a subset, or it is not a subset, we will see it once we are reading the general statements and definitions. This sign, which is, it's like an A with, a dash. It's like this. Sometimes you will see it like that, or you can see it like this. It means it means for all or for every. You can read it as for all or for every. Also, this is equivalent. This is there exists, and this is there doesn't exist. So there exists a condition, or there exists a value. This there doesn't exist. You will have more than one example on each statement of these statements. Those symbolizations will help you out when you reading either a problem or a part of a statement or something like this. Okay. Now I will go through a simple definition, the simplest definition of vectors. What's a vector? Okay. What's an arranged pair? We will use the word vector plenty of times in this chapter. So a vector X in the plan, if I'm talking about a vector in a plan, is presented geometrically by a directed line segment whose initial points is the origin and those terminal points is the point that we are indicating. Usually we can say it's a position vector, but for us we will consider it as a vector. But mainly, maybe in your previous studies, you have studied this as a position vector. So, for example, or for a quick remark, if I have, for example, 1 and 2, I can write the vector 1 and 2, which means a position vector between the point 0, 0 and the point 1 and 2, for example. Okay, the bullet at the end of the arrow, it's the terminal point x1 and x2. This vector is represented, as I told you, x is equal to x1 or x2, which means a coordinate in the x and another coordinates on the y, or x1, y1, two numbers, 3 and 4 and so on. But mainly it contains how many coordinates? 2 coordinates. That's the case of what's called the vector in 2 dimension. 2 dimension, it means a plan. What's the plan? This is a plan. Okay? This face is a plan. It's a regular part and it is a planar surface. So this is a plan. Of course, if we have more coordinates, we will move into from 2 dimension into 3 dimension, as we will see. Okay? Step by step. The second thing that I want to review with you, when 2 vectors, or what's defined by vectors, is equal to each other. When can I say that u vector is equal to v vector, Omar? They will be equal to each other, okay, if their corresponding coordinates are equal. So if I say when u is equal to v, it means u1 is equal to v1, u2 is equal to v2. That's the meaning of a vector equality in 2 dimension, or in 3, or in 4, we will generalize it. Okay, how to do an addition of vectors? We are adding the corresponding coordinates. So if I'm adding vector u, which has 2 components, to vector v, which has 2 components, the result will be, I will add just only the first components on each other, then the second components on each other. And this is how we are going to get the result of this addition between 2 vectors. It's really very simple. How to do a scalar multiplication? If I want to multiply a scalar, which is a constant value, in a vector. So this constant value will be multiplied in all the coordinates. Yes, Adam, it is really very near to the concept of row matrices, if you remember. Do you remember the matrices issue? Do you remember the row matrix, which is a matrix with 1 row and more than 1 column? When you add them together, when you multiply by a number, remember all of these properties. It's really very close to vectors, okay? So the scalar multiplication, if you multiply scalar, which is a real number, multiplied by v, which consists of 2 coordinates, for example, Salma, it will be multiplied by the first coordinate and the second coordinate. Those are the most important and the simplest properties, related to vector issue. Okay? Okay, the discussion of vectors in a plan can now be extended to a discussion of vectors in n spaces. All of our visualization, it's between R1, R2, and R3. Most humans, or most of us, or all of us, will have a visualization for R1, R2, and R3. R1, it's simply a straight line. Okay? The x-axis, for example. The x-axis, if you remark, it's a real number, it's r, which starts from negative infinity up to positive infinity, going through the 0. All the coordinates, it contains just only one number, so usually it is r1, which is the x-axis. The second thing, Mr. Ziad, is r2. R2, it is the surface. Okay, it's the plan. So you have x and y. How many coordinates? 2 coordinates. This is why we say this vector belongs to R2. Okay? So I can say for a plan values or coordinates that the point or the vector xy belongs to R2. X belongs to R1. And I can say also x, y, and z belongs to R cubed, which is R3. In this case, I will be moving between a plan and the 3 dimension. Okay? This is the x-axis, y-axis, and the z-axis. All of us visualize in 3 dimension. More than that, it's gonna be hard on us. for most of the units. Okay? Why we are saying this? Because if I'm talking about 4 dimensions, you can feel X, Y, and Z and time. Okay? But I can generalize it to n dimensions. So I can talk about R4, R5, R6, R7. Once you hear R7, it means that the vector will contain how many components? 7 components. The first, second, third, and so on. And so on. Same properties, it's already contained. So it's the equality, the addition, the multiplication by scalar, it will be all the same. So the set of all ordered n tubules is called the n space and is denoted by Rn. This is R1, as I told you, a set of real numbers, which is, for example, as a line like the x-axis. R2, which is a 2-space set of all ordered pairs, x1 and x2. If I'm talking about R3, it will be x1, x2, x3, or xyz. If I'm talking about 4, blah, 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 and so on, up to you reach Rn. This is for the n-dimension coordinates, or vectors. Also, or just only for training purposes, this is away from the questions that we will face, but just in case to just stress on the fact of addition, multiplication, and so on. If I want to get the value of W, how to do it? I need to know what's the value of W that will make this equation correct. Any ideas how to do it? Huh? I need the correct value of W, or what's the value of W? That will make this equation, which is simply 2U plus V minus 3W equal to 0. If I were in your shoe, the first thing that I will do, I will try to separate W on one side and all the other vectors on the other side. So simply, I can move really, very, very easy. Doing this, it's gonna be 3 of a W, which is gonna equal to 2U plus V. If you remark, I've just moved negative 3W to the other side. So I have now 2U plus V is equal to 3W. So simply, W will be 2/3 of U plus 1/3 of V. So all I have to do is to multiply the coordinates of the U vector in 2/3 plus adding the 1/3 on the product of the coordinates of V. This is what I'm going to do. Okay, Ms. Judy? So this is a 2/3 times U plus 1/3 times V. I've taken U, which is 0, 0, negative 8, and 1, multiplying all the coordinates by 2/3, then I will add 1/3 on the coordinates of V, which is 1, negative 8, 0, and 7, which is very, very simple. I will multiply 2/3 times 0 plus 1/3 times 1. And this reflects how important the matrices are. Already this process you can do it by your eyes, okay? Because it's exactly like adding 2 row matrices multiplied in constants to each other. Are you with me? Okay, so the result is simply, as you can see, it's 1/3 negative 8/3, negative 16/3, and 3. It's very, very simple. Okay. Now I will start talking about our main topic today, which is a vector space. This need to be really well understood. What's a vector space? A vector space, it's a collection of vectors or objects. It's like a set. A set is a collection of something. Okay? A set is a collection of some stuff. I can get them all together in one room. Our room, it is the set. So, vector spaces, it is defined in this tab. A real vector space V is a non-empty set. Stop. What do you understand? I have a set, but it's not empty. At least it will contain the 0 vector. What's the 0 vector? From any dimension, it's gonna be just representing this dimension, but all the coordinates is equal to 0. So the first piece of information. A vector space is not an empty set. Why it's not an empty set? Because it contains at least the origin. Okay, so a vector space, V is not empty set. Whose elements, meaning elements اللي موجودة فيها, whose elements are called vectors. So if I'm talking about R1, it's going to be a collection of numbers. If I'm talking about R2, it's going to be a collection of ordered pair, but with 2 coordinates. If I'm talking about R3, so it's going to be just a bunch of vectors. Each one of them contain 3 vectors. Okay, so once more. A real vector space V is a non-empty set whose elements are called vectors, in which there are defined 2 main operations. All I need to know that there is 2 main operations are defined on this set. The addition and the multiplication by scalar. So, once more, let's repeat what I said. I have a set. This set, I usually move my hands like this because a set usually take these type of parentheses. So, it's a set of some vectors. The vectors inside this set, okay, at least it will contain 1 vector, which is the 0 vector. Then it will contain more vectors in it. Those vectors are defined on how many operations? 2 operations. The addition operation, you saw the addition operation. That when we add 2 vectors together, that means we are adding the corresponding coordinates in each one of them. And the second operation is multiplication by scalar. And also you saw it. If I multiply a coordinates or a vector, all its components will be multiplied by this vector. So these 2 operations. Okay, I will define what I say, but by statements. So for every u, v, and w, how many vectors now I'm giving you? 3 of them, u, v, and w. That belongs to the vector space V, which is supposed to equal to V. And for every A and B, equally A and B, which belongs to the set of real numbers. So what are A and B? What are A and B? The set of real numbers, and B is the set of real numbers. So it's from negative infinity up to positive infinity. Do you understand? Okay, such that the following properties are going to be held. The first is the addition of any 2 vectors. The result will be a vector in V. بس مجرد انك تفكر في اللي انا قلته لك ده، يعني مجرد انك تفكر في الستيتمنت ده هتتخيل قد ايه V is enormous. يعني الفيكتور سبيس ده حاجه ضخمه جدا جدا لدرجه ان اي 2 فيكتورز فيه تجمعهم على بعض الريزلت هتبقى فيكتور موجود فيه. متخيل الست دي ضخمه قد ايه؟ يعني ست it's a huge set. Okay? So this is number 1. This is the addition property that we spoke about. Okay. During this or within this additive closure, which means the result belongs to V, also the associativity, which means I can distribute the addition of 3 vectors just to get V and W first, then adding to U, or get U and V and then adding to W. The commutativity, which means U plus V is equal to V plus U. The 0 existence, there exists. This is why I've given you all the symbolization at the beginning. There exists a vector 0, or the origin belongs to the vector space V, such that V plus 0 is equal to V, which means the 0 vector, or the existence of the identity of addition, okay, which is 0, the null. Also, it must contain the symmetry or the negation. What's the symmetry or the negation? The inverse of the numbers, or the opposite sign of the numbers of the coordinates of a vector. So there exists, for each u, there is also exist negative u, such that when you add them together, the result will be 0. If you remark, those five properties are related only to the addition measure. So how many properties, when I say addition closure, those 5 elements must exist. So what we mean about addition closure? That the result will exist in V. That it can be distributed. It is commutative. The existence of the negative element. the existence of the null. I've spoken now about the addition of two vectors, or the addition process. I will continue with the multiplication by scalar. Once you start multiplying by scalar, and once more, remember that A belongs to the set of real numbers. So all the real numbers. So if I multiply A times B, the result will also belongs to a vector, this vector space. Can you imagine now how it is big? It's not just only a small set of elements, it's a huge set of elements. Under the condition that the addition of any two vectors in it, the result will belong to this vector space, to this collection. This is the multiplication by scalar, the distributivity of scalars, the distributivity of addition of multiplication by scalar. Same way like if I have two scalars and I'm distributing on one vector, to really hold. And the existence of the identity of multiplication. What's the identity of multiplication? The unit vector, or the one. When you multiply V in one, the result will be V. Do you remember what was playing the identity rule in matrices? Unit matrix, okay? So if you look at all of this, those are the conditions that should exist in if you are studying some relation to be a vector space or not a vector space. So once more, what's a vector space? It's a collection of objects. They all look like each other, okay? Under how many operations? Two operations. What are the two operations? Addition, closure, and the multiplication by scalar. Under the addition closure, you have how many property to test? 5 of them. The addition, the distributivity, the associativity, the commutativity, but the most important ones, the existence of the negation and the origin. This is for the addition. For the multiplication by scalar, you should check how many Karim? 5 of them. That the result of multiplying by a constant really belongs to the set, the distributivity properties, and the most important ones is the existence of the negation. Of the identity of multiplication, the existence. So whenever I ask you, if this set represent a vector space, what are you going to do? You are going to check all of this, okay? A failure in any one of this, this is not going to be a vector space.
Yeah.
Okay. Any questions? Okay. Let's see examples on vector spaces. The first example on vector space is R1. This is R1. Imagine the real number. The simplest thing. Imagine the x-axis. If you have the x-axis, okay, what are the numbers on the x-axis? The points, the coordinates on the x-axis. 0, 1, 2, 3, 4, -1, -2, -3, and so on. Try to think about the 10 properties that I told you about. First of all, the existence of a 0. 0 exists. If you add two values, the result will exist belongs to the x-axis. To the set of real numbers. If you multiply any number by a constant, which is a real number, the result will belong to real numbers, and so on. So all the probabilities hold for R1. Okay, for R2, R2 means the plan, which is x and y. Okay, imagine x and y plan. All the coordinates with how many components? 2 components. And think about the vector space, the commitments that I told you about. It contains a 0 in the middle, صح? And also any point, if you add it to any point with 2 coordinates, the result will be 2 coordinates. So it will still belongs to R2. If you have any point or any vector, like 3 and 5, for example, Ms. Judy, the inverse or the symmetry of this vector already exists. So if I have 3 and 5, -3 and -5 also exist in R2. So it's a vector space. Same discussion can go for R3, which X, Y, and Z. Also, for any larger than this, by the idea, I can write them in this manner. Say R2 is equal to the set of all vectors which consists of how many coordinates, such that X and Y belongs to me, to R. Look how it is written. Ziyad, the way R2 is written, I don't want you to just memorize it. I want you to understand it in order to be able to write it on your own. This is R3. Biologic. R3, how many components? So it's going to be X, Y, and Z, such that both triple components, X, Y, and Z, belongs to the set of real numbers. This is R3. By generalizing, I can get to R5, or R6, or R7. معايا أحمد? So R5 will contain how many coordinates? 5 coordinates. The 5 coordinates belongs to R, same way like. Also, the set of matrices. Let's say the set of matrices 2 by 3. The set of matrices 2 by 3. Which means all the set of matrices of how many rows and the 3 columns. Please, think about the 10 commitments. For all the matrices with 2 and 3, is all the probabilities hold? فكر كده يا هدف. For all matrices of 2 by 3, لكل الماتريسيز 2 by 3. بص سلمى, first thing, 2 by 3, one of the matrices of 2 by 3 is the origin, 0, 0, 0, 0, 0, 0. So the origin exists. How to add 2 by 3 matrices to each other? The corresponding elements will be added to each other, and the result will be 2 by 3. If I have 2 by 3 matrix and multiply it ya Omar by a number, the result will be 2 by 3 matrix. So all the conditions, all of them already exist in matrices 2 by 3. Okay, similar to 3 by 3, 4 by 4, 5 by 5, 5 by 6, and so on. But as long as the conditions, all the conditions hold. So all of this are vector spaces. This is, of course, خلاص for Rn, also for the set of matrices m by n. Okay, is the set of diagonal square diagonal matrices represent a vector space? If this set represent a vector space? فكر. ها جودي. A set of m by n diagonal matrices doesn't represent a vector space. أفكر إزاي؟ أبص على الdiagonal matrix, any diagonal matrix. أولا, first thing, does it contain a zero matrix? Yes. It's going to be diagonal, but all the elements are zeros, so it already exists. If I have a matrix 1, 1, 1, 1, okay, 4 by 4, its inverse will exist. Negative 1, negative 1, negative 1. If you added them together, the origin will appear. Am I right? If you have a diagonal matrix and you add it on another diagonal matrix, the result will be diagonal matrix, because you are adding elements correspondingly. Okay, if I have diagonal matrix from any dimension and you multiply it by a number, the result also will be diagonal matrix. So yes, it belongs to the set of or represent a vector space. Once more, you will have to review all of this. Okay, remark. Let V be a vector space. So we are not discussing if V a vector space or not. It is a vector space. What I'm going to gain, or what's the remarks that I will have with this vector space? Okay, for each vector, its symmetric is unique. Miss Judy, what's the meaning of a symmetric of a vector? The inverse of this vector. The inverse in sign. So if I have the vector, if I'm talking about R3, like 1, 2, 3, the meaning is I will have negative 1, negative 2, negative 3. If I have 0, 1, 0, then I will have also 0, negative 1, and 0. So if I have a vector space, all the elements in this vector space, its symmetry already exist. Okay, if I multiplied A by the 0 vector space, the result will be the 0 of this vector space with relative for every A belongs to R. Also, the 0 of any vector is the 0 of this vector space. Multiplying by a number, any coordinates in a vector, the result will be the vector belongs to V. A times V is equal to 0. Now A times V is equal to 0, it means either A is equal to 0 or V is equal to 0. These are the main remarks that's related to if you have mainly a vector space. Okay. Who will solve this problem with me? Omar. Mr. Omar. Let's look to this set. V is the set. Ziyad. V is the set. V is the set. Okay? Of all x and y. Where x and y belongs to me? To R. So I'm talking about V, which is the set of x and y, such that I'm not going to take all the real numbers, but I'm taking x is greater than or equal to 0, and y is greater than or equal to 0. The space these conditions represent, can you imagine this space? I'm talking about coordinates in R2, am I right? X and y. But under the condition that x is greater than or equal to 0 and y is greater than or equal to 0. So I'm talking about the first quarter only. This is the set that I'm considering. Instead of considering all R2, my vector space study now is a vector space or a set of collection of elements that belongs only to the first quarter. Does it, يا جودي, represent a vector space? Or they represent a vector space? تعالي think together. Let's take a point, if I will. Let's take a point. Belongs to this vector space. Which point would you consider? Let's say 1, 1. And I will take another point, okay? Which is 2 and 3. If you add them together, please add them together. What's the result gonna be? 1 plus 2 and 1 plus 3 is gonna be? So the result will be, which belongs to this set, am I right? Okay. If I want to, if I have another vector, and if I added them all together, also under the condition that both values are positive, the result will be positive also, am I right? Okay. Does it contain the origin? You remember the 10 commitment? Does it contain the origin? Let's check. Within this Q1, you started from x is greater than or equal to 0 and y is greater than or equal to 0, which means 0 is one of the elements. So 0 exists. So if I am checking, okay, if I am checking the conditions, the addition is okay. So the additive associability is okay if you have 3 vectors. The commutativity also exists. Instead of adding 1 and 1 and 3 and 4, I can add 3 and 4 plus 1 and 1. The result will be the same. Okay. The 0 existence, am I right? The 0 already exists, am I right? Okay. Let's look to this guy. Does it exist? For any vector, its inverse exists. If I took 1 and 1, what's the inverse of 1 and 1? According to this definition, negative 1 and negative 1. Negative 1 and negative 1 will be here. If this point belongs to the set, this is the set that I'm talking about. If this point or this vector is a part from this set, معايا زياد؟ هي فعلا بتنتمي للفترة دي؟ لا. يبقى على طول it's not a vector space. يبقى مجرد one failure in the 10 commitments, it means this is not a vector space. يبقى for this set, it's not a vector space. Why it's not vector space? Simply because property number 5, which represents a multiplication by a negative value, doesn't exist. Also, if you think just a little more, you will find if you multiply A belongs to V, is the result gonna be V? No. Because A belongs to the set of real numbers. Any scalar multiplication, it means the value is gonna be belong to real numbers. Real numbers contain the positive part and the negative part. So if you multiply any value in here, like 1 and 1, multiplied by negative 2, it's gonna be on the opposite side. So it doesn't belong to this interval. So it's done. So solution, in fact, V is not a vector space. Not every element in V has an additive inverse, which means, if simplest example, if you have 1 and 1 multiplied by negative, it's going to be negative 1 and negative 1. This is why it's not a vector space. Okay, once more. Let V be the set, Ahmed. let V be the set of all elements 2 by 2, but under one condition. That's X for the first component. The second component is half the first component. By the idea is here, I can give it to you like this, and also can give it to you in this manner. I can give it to you like this. I can say V is the set of all coordinates X and Y, such that Y is equal to half of X. That's the set that we are talking about. And of course, X belongs to R. It's going to be the same, because all I have to do is to replace Y by half of X. Now, let's think about this situation. I'm talking about X and the half of X. The set of all elements, which has a special property. The Y coordinates is half the X coordinates. Is this set represent a vector space? What to do? I'll think about in commitments. فعليا أنا لو أنا عندي 1 and 2 1 and half, and they have 3 and 1 and half, add them together, you will have 4 and 2. صح? So it's still property holds. If you multiply in a number, in a constant number, it will hold. If you have 3 values and you added them together, it will hold. The existence of an origin, if X is equal to 0, you have 0 and 0. So it already exists. I didn't talk with you about positive values or negative values, so all the real numbers exist. So if I have, for example, 1 and a half, and multiplied by a negative, it's going to be negative 1 and negative half, which means it belongs to the same set. Am I right? Multiplying by any number or by any constant, which means the 10 commitment already exists. This is represent a vector space. So once more, those are the 10 commitments. Yes, V is a vector space. We checked all the properties in 4.21, all of this, and they are all exist. This is the addition of 2 values, X plus half of X, Y plus half of Y, and this is going to be the result, which is correct. If you multiply by